Made me realize that I need a fresh up on.
Yeah, very good. Very nice, which was kind of the goal behind the quiz. What else? Like, were you confident at least for parts of the question, or was the whole thing like a nightmare? Nightmare? Oh God, don't say that. What about you guys?
For a couple of questions.
But-
And, a couple of the other ones wrong, and I was also confident.
Okay, Nate?
I knew like half of them and I forgot the other half. I don't even think I did like two of them, like we did. Like we didn't even do two of them.
Like, didn't even attempt
No,
them?
because they didn't even look familiar. At least the
Really?
ones, they looked familiar, but those didn't even look familiar.
Okay, that's interesting. Yeah, and we'll take a quick look at the quiz. Any other feedback from you guys here? No? Okay, so definitely, like I said, the purpose of the quiz was to kind of gauge, how confident you are with your college algebra skills, maybe where, like you said, some you didn't even recognize if you had actually done them or not. So that would be something to go back and definitely review. So as I was telling you guys last time, chapter P in your textbook is that prerequisite chapter. We're not working on it, but if you wanted to go back and you look at concepts so you could be comfortable, then I would definitely recommend you guys to do that. So just to look at the quiz, of course, your numbers would be a little different, but the questions are the same. So for the first one, you needed to know the distance formula, which, again, I know if you don't remember it, that's okay. But the distance formula is the same formula you would use if you were trying to find where the center of your circle is. So if you knew like 2 points on your circle, sorry, not the center. If you knew the center and a point on the circumference, then you would use a distance formula to find the radius. So that's kind of why we use the distance formula here, because, of course, we're going to be working with circles, and that's something we're going to come across. This one, as you can see, was an absolute value equation. So if you remember about absolute values, that's basically the distance from 0 on a number line, right? So the idea is, if we are trying to figure out what this distance is, which is given to us in the generic terms of 5x plus 2, remember that distance can be on the positive side of the number line or the negative side, right? Because you could go in either direction on the number line. So that's why absolute value always gives you two answers, because you don't know if you're heading to the positive side of the number line or negative. So that's kind of one thing to keep in mind with absolute values. And then, this one was just a general algebraic function. So this was your cubed function. You can see y equals x to the third minus 8. The concept of symmetry is also something we will be talking about, but basically, again, falling back on college algebra, when you have an even function, which means all the exponents in your equation are going to be to the even power, so second, fourth, eighth, those are going to be symmetric with respect to the y-axis. If you have odd functions, which is what this equation is, because you have x to the third power, so that's 3, and this is technically 8 to the first power, so again, 1 would be an odd number. So this is an odd function, and odd functions have symmetry with respect to the origin. And the easiest way to remember is O goes with O, so odd with origin, and that's a symmetry. So even functions have symmetry with respect to the y-axis. Odd functions have symmetry with respect to the origin. And then remember, we also talked about parabolas in college algebra. Parabolas have their own symmetry, so they will actually bring their own axis of symmetry also. So that could be an exception to this. And then, of course, they're asking you to identify which function is going to be which. This actually also takes us into transformation, guys. If you did not have the -8, then your x to the third would actually be passing through the origin of the coordinate system. But because that is -8, it's actually telling you your graph has moved down by 8 units. That's that vertical translation we talk about in college algebra. Again, we'll be talking about transformations here also. So it's actually going to be, trying to think, x to the third. So it should be graph, that second one on the top, on the right-hand side. But again, you guys can use graphing calculators. So if you didn't want to graph by hand, you can just use Desmos to do that. This one you can see is a square root function. So remind me again, what restrictions do we have when we're working with square roots? What can you not use for the X value?
Negatives.
Negatives, right? Because that takes you into imaginary numbers once you start going into negative. So inside of a square root, you cannot have a negative number, which would put restrictions on what kind of numbers you can have for X. Which this one was just asking you to, take those numbers in the parentheses and put it in for X and see what answer you came up with. But this one, you can see again, we go back to absolute value functions over here. So this one was basically asking you to identify what the parent function would be. And your parent function honestly would just be the absolute value of X. Everything else is transformation. So this is telling you the +1, that your graph actually moved 1 unit to the left. The negative is telling you it got reflected. The 3 is telling you it got stretched. And then the -4 is telling you it moved down by 4 units. So these are all transformations. So vertical translation, horizontal translation, reflection, stretching, and shrinking. So transformations, like I said, is going to be a big part of what we talk about also with the trig functions. And again, obviously they were asking you to select the graph on that. This one over here is composition. Now, composition, guys, remember that is where you take one function and put it inside of the other one. So when they basically tell you f of g, that means you're actually taking the g function and putting it inside of f. So the idea is you would actually solve the g function first, get the answer from that, and then whatever answer you get from g is what becomes the input for the f function. When you reverse the order, that means you solve the f function first, get the answer from that, and then whatever result you get from it, you put it inside of the g function. So that's what composition does. And this one, of course, is g of g, which means you're working with the same function, but you still start with that second g, which would still be the same function. You would solve this first, whatever answer you got, you put it back into itself. So that's what the composition would do. This one is asking you to find the inverse functions. Now, inverse functions is also something we will be talking about with trig. So inverse functions is where, like for addition, its inverse function is subtraction. For multiplication, its inverse function is division, right? For square, the inverse is square root. So whatever the first function will do, the inverse function will undo that operation. So in this case, as you can imagine, there's a square root, there's a multiplication with 4, there's an addition with 2. So when you were to find its inverse, you would have to reverse that addition, you would have to reverse that multiplication by 4, and you would have to reverse the square root. So all 3 functions would have to go. And this one is where I would recommend, if you guys have not looked at the switch and solve method for finding inverses, that might be a good one to review. Just so you are comfortable working with inverses. And then, of course, we'll talk about how all of these different concepts apply with trigonometry. Some things will be different, but most of it will be very similar. So you can see all the questions that were selected in the quiz are going to be concepts we will be coming back to in trigonometry. So just, use your textbook. And again, this is the instructor mode, but on your student side, remember on the top banner, it gives you the My eBooks option. And then also on the right-hand side of your screen, it gives you that little image of your textbook. This guy will pop up. Oh. Sweet time. There we go. Yeah, so you can go under My Books at the top, or like I said, on the right-hand side, you can see you have the image of your textbook, so you can go from there also. All righty, folks, let's get into our. I thought I had opened our handout. Oh, I know this. that big enough, or do you want me to make it larger? I guess that works better. Alrighty. So let's take a look at this guy here. So, initially when we talked about trigonometry, it was basically working with triangles, right? How do you solve triangles based on their sides and angles, right? But obviously trigonometry has grown much, much bigger than that. Since then, of course, now we have applications, of course, astronomy, navigation, surveying, but with all the new sciences, the world of trigonometry has expanded a lot more. So now we can talk about, sound waves, basically any kind of wave motion, honestly, planet orbits, vibrating strings, pendulums, even at atomic level, orbits for the atomic particles, which kind of mimic those planetary orbits in a way. So a lot of different applications when it comes to trigonometry. And as I was telling you guys last time, trig is kind of the stepping stone when you're trying to get into calculus also. So let's get familiar with some terminology over here. So one of the basic things we'll be talking about is, how you work with angles. So if you take a ray, which is basically half of a line, because one end is going to be closed, and then, you have the arrow at the other end. So basically one end is going to be closed, but then this one can, keep expanding. So that's a half a line or a ray. So basically the idea is you start at the starting position, and we usually talk about the starting position being right over here, which means it's going to be on top of the positive axis if you superimpose it on a coordinate plane. So, think about where the positive x-axis would be. So that would be the starting position of your ray, and then you rotate it counterclockwise to get positive angles. If you rotate it clockwise, you are actually going to get negative angles. So keep in mind, this direction that we're going in is counterclockwise, which will give you positive angles. So depending on, okay, we start at the initial side, we start rotating our angle, where you stop, that becomes the terminal side. So that's going to be your standard position for an angle when we're talking about this. And this is going to be true with all kinds of applications that we are working with. So this is always going to be your standard position. Now, for Greek letters, we use small letters, alpha, beta, theta for angle measurements, or in the Roman letters, we will do uppercase A, B, C for the angle measurement. So just keep that in mind. Alpha, beta, theta would be in the Greek letters, and then capital A, B, C. And of course, if you have multiple angles, you just add the letters to that. So the way this will work out is basically, so we took our initial side of our angle, and you can see we went in the counterclockwise direction, came to our terminal side. So technically it actually ends up making two angles, because you have one angle on the counterclockwise side, but you actually have another angle on the clockwise direction. Or you can just go in the same direction also. So if you go in the counterclockwise direction once, this makes an angle, but you can actually make a complete circle and come back to the terminal side, and you can still make another angle. These are what we call as coterminal angles, because they are sharing the same terminal side and the same initial side. So you will actually see this as a question in your homework, where they will ask you to identify coterminal angles. So remember, you can go basically in the counterclockwise and clockwise direction. So that will give you the two, one positive, one negative angle here. Or you can go in the same direction, but you are basically completing a circle, which means it will be, 360 plus whatever that extra is. And they become coterminal angles. So in this case, they would both be positive angles. In this case, one would be positive, one would be negative. So those would be your coterminal angles. And I believe they actually do ask you to find one positive coterminal and one negative coterminal angle. Now, one of the common measurements that we use is radians. Of course, we talk about angles in degrees, but you will see we actually do more radians when we are working with trig. And of course, once you guys get into calculus. So again, over here, we're basically saying the amount of rotation from the initial side to the terminal side would determine the measure of an angle. So basically, you know, how far that ray has moved will determine your angle measurement. And basically, one of the measurements we're looking at is radians over here. Now, we're basically saying when you are trying to define a radian, use the central angle, which will be this angle over here, which is going to be the angle made by the vertex. So this is the vertex, you know, where that initial ray ends. So the angle whose vertex is the center of the circle shown. So starting from here, you know, this is our initial side, this is our terminal side, and this will become your central angle. So the way we define radians is basically we are saying if this arc length, so that's this little distance over here, if it is the same as the radius of your circle, then that means your angle is going to equal 1 radian. So basically the idea is the radius of your circle and this arc length have to be the same measurement, and then we can say this angle is going to be 1 radian. And you can see in that little box over there, the way we are defining radian, we're saying 1 radian is the measure of the central angle theta that intercepts. So basically it's, you know, crossing the arc S an equal length to the radius of the circle. So basically the radius of the circle has to be same as that arc length. And then you can define theta as S divided by R. So, you know, and obviously if S and R are the same measurement, S divided by R is going to end up giving you 1. So your theta will end up becoming 1. So to break down what 1 radian would look like, you want to think about in terms of the entire circle. So let's take a look at this image over here. So in radians, we define the circumference of a circle to be 2 pi r. So 2 pi r, you know, of course, will be equivalent to 360 degrees in the degree measurement. So if you take the radius out for a minute, then we know 2 pi is approximately 6.28 because that 2 times a pi, and we define pi as 3.14. So 3.14 times 2 would be approximately 6.28, right? So that means you have just a little over 6 radius lengths. So that means you can take 6 of these central angles and then, you know, have that 0.28 left behind. So an entire circle can technically be composed of 6 radians in there, you know, following that definition that we just saw over at the top. So the idea here is then, you know, we can kind of break it down based on what those, you know, depending on where your angles end up going. So that's kind of something you want to think about. And in this case, we're basically saying S divided by R, since they will have the same measurement, you're not really going to have any unit of measurement per se, like, you know, we normally do with distances like meters, inches, you know, any of that. You're not going to have any of that. So we're basically saying the measure of an angle for 1 full revolution, which means going around in 1 full circle, is going to end up being that same definition we saw on the top, S divided by R. So in this case, since our entire circle has a circumference of 2 pi r, your S, the arc length for the whole circle, will be 2 pi r. Divide that by r, and you end up getting 2 pi radians. So basically, we are now trying to break down that 2 pi into smaller sections. And this is where that unit circle I was talking about last time will come into play, because then it will show you how those angles are broken down. So remember, 1 full circle is 2 pi in measurement as far as radians go. If you take half of that, which means 2 pi divided by 2, you're going to get a half a revolution, which means you're only going 180 degrees, and that's going to be a measurement of pi. That's what they're talking about here. If you go a quarter of a revolution, so instead of going, you know, the full circle, or instead of going half, if you're only going quarter, that's going to be this one. So that will be 2 pi divided by 4, which will give you pi half. So that's going to be your 90-degree angle right there at pi halves. 1/6 of a revolution, which will be even smaller. And as you can see, 1/6 is going to be 2 pi divided by 6, which will give you pi over 3. And then, of course, you can break it down into further smaller angles, 45 degrees, 30 degrees, which is what that pi over 4 and pi over 6 is going to be. So depending on how many revolutions you are going, that angle is going to change. But if you can remember that the entire circle is 2 pi, you can basically say, okay, am I doing 1/6 revolution, 1/8 revolution, 1/12 revolution? Based on that, divide the 2 pi by that number and you'll get your radian measurement. And then, think about this being superimposed on top of your coordinate plane. So let me. This should be good enough. So basically, when you are coming a full circle, we go in our counterclockwise direction, we come back. The 0 degree or the 0 radian, it also corresponds to 2 pi because now you've made a full circle. So this will also be 2 pi right over here. And you can see when you go half a revolution, you're at pi, which of course is a straight angle, 180 degrees. If you go a quarter revolution, you're at pi halves. Because, of course, you're going half that distance. So pi halves, that corresponds to 90 degrees. This was your, this one was your 1/6 revolution. This one was, what would be 1/8. And this guy is 1/12 of a revolution. And then, of course, you will see as you go forward, what those measurements are going to be in radians. But the idea is, to start thinking about more in terms of radians, because that's what we're going to be using. And then, again, you can see how they're breaking this down into a coordinate system. So you have your quadrant 1, quadrant 2, quadrant 3, quadrant 4. So if you think in terms of angles here, you can see we're going from 0 to 90 degrees. So quadrant 1 is going to be all acute angles because they are going to be between 0 and less than 90 degrees. When you go to quadrant 2, you are of course going to be between 90 degrees and 180 degrees. So you can see these ones over here will be obtuse angles because they'll be larger than 90, but of course less than 180. Then you are going from 180 to, if my memory serves me, I think that should be 270. So between 180 to 270 degrees would of course be quadrant 3, and then coming back, remember this is also 2 pi, which is the same as 360 degrees. And you'll be coming back between 270 to 360 degrees over here. And then remember how in coordinate, just an X and Y coordinate system, remember how both your X and Y values are positive in the first coordinate quadrant, sorry. This one over here, X is negative, but Y is still positive. This one over here, what is it? Both are negative. And then this one over here, X is positive, but Y is negative. Well, here's what happens. With this guy. So you will see both positive coordinates over here. You will see X is negative, Y is positive. Both X and Y are negatives over here, and then positive X, negative Y. So again, you're just bringing that same knowledge that you had from college algebra into trigonometry over here. All right, so they're basically saying the phrase that theta lies in the quadrant. Is basically they're saying it's an abbreviation for the terminal side of your theta lying in a quadrant. So basically, where the terminal side ends up will tell you which quadrant your angle is going to be. Because remember, your initial side is always going to be on that positive X side. So it's basically where that terminal side is going to be, which tells you, are you in quadrant 1, quadrant 2, quadrant 3, quadrant 4? And then on the axes itself, those are what we call as quadrantal angles, because they don't belong to one or the other quadrant. So 0, pi halves, pi, 3 pi halves, those would be the angles that we would call as quadrantal angles. Of course, you can see that's going to be 0 angle here, pi halves here, pi over here, and 3 pi halves over here. So they don't belong to any quadrant. They are called as quadrantal angles. Alrighty, so we talked about coterminal angles. Basically, remember, they have the same initial side and the same terminal side. Now, 0 and 2 pi are coterminal angles because obviously they share the same initial, same terminal side, which just happens to be that one single line. Your angles, pi over 6, 13 pi over 6 are also coterminal, and that actually means you did pi over 6 and you just added 2 pi to it to get 13 pi over 6 because you went in the whole revolution and came back to it. So basically we're saying to find an angle that would be coterminal, you can either add or subtract 2 pi, which means that one entire circle, that one entire revolution. And then that's what we're kind of looking at over here. And honestly, you can do that in multiples. You can add 2 pi, you can add 4 pi, you can add 6 pi because you keep making those revolutions. So technically, we can basically say you can add or subtract 2 pi n, which means that n tells you, are you doing 1 revolution, 2 revolution, 3 revolutions based on that. So let's take a look at this example over here. So we are given the angle positive 13 pi over 6, and we want to find its coterminal angle. So in this case, we actually end up subtracting 2 pi from 13 pi over 6, which ends up giving us just pi over 6. So basically what happened here was, this angle by itself here, just that one single, going from initial to terminal side was the pi over 6, but we were actually given 13 pi over 6, which meant you were actually going this full revolution. So this whole movement was where that 13 pi over 6 came from. And then when we subtracted 2 pi from it, we basically, what we did was we subtracted this whole revolution because that forms a circle. We subtracted that from it and it only left you with this section here, which is what this guy was. And that's where the pi over 6 comes from. Now, as far as math goes, you will have to take this, like you subtract fractions. So you would think of this as, okay, this guy's over 1. If I want to find a common denominator, I multiply this side by 6. So that would end up giving us 13 pi over 6 stays as it is. 12 times 2, 2 times 6 would give you 12. And then you can see 13 minus 12 will give us 1. So that just becomes pi over 6. So as far as adding, subtracting these numbers go, you are treating them as just fractions, and then that pi just kind of goes along with you. For the second one, they are actually giving you a negative angle, negative 2 pi over the 3, negative 2 pi over 3, and they're asking us to find a coterminal angle. So for that, we're adding 2 pi in this case, and you will see that will end up giving you a positive angle, 4 pi over 3. So what's happening in this case is you're going in the opposite direction. So when you're saying it's negative 2 pi over 3, that actually means you went in the clockwise direction. So by adding 2 pi, you're actually finding the other side of it, the positive angle for the same initial and terminal side. So let's try and do our own examples over here. We have theta equals 9 pi over 4 for the first one. Do you not want to work for me? It worked the other day. I'm not sure why it doesn't wanna work right now. Okay. So this one is just telling us for each angle to find one negative and one positive angle. So let's start with the positive. What would we do to find the positive angle? Man, I keep, I'm not sure how this is. moving. So tell me, what do you get when you add 2 pi to this? Because we want to find one positive and one negative coterminal. Okay. Oh, sorry, 2 pi. So same thing, you would need to start by finding common denominator. Multiply by 4, since that's the other one. And you end up with 9 pi over 4 plus 8 pi over 4, and you can see that's where that 17 shows up from. Okay, so that would be the coterminal angle. I don't know, I'm gonna call it theta sub c for the coterminal. And this will be 17 pi over 4. What would a negative coterminal angle look like? Can we just subtract 2 pi from it? No? What happens when we subtract 2 pi from it? Yeah, because this angle is actually more than 360 degrees, right? This is an angle larger than, so even just subtracting a simple 2 pi doesn't actually give you a negative answer, because this would still be, come on, buddy. Just 8 pi over 4, which is still small enough, like you said, this would only give us pi over 4. So how would we need to change that so we can actually get a negative coterminal angle?
Do it one more time.
Yeah, exactly. Perfect. So we did one revolution, but it just gave us a positive, and technically you can use that for the positive coterminal also if you wanted to use. But basically do one more revolution. So subtract 2 pi again, or originally start by subtracting 4 pi. Either way. So in this case, since we already did one subtraction, we'll just start here and subtract another 2 pi from it so that we can get our negative coterminal. So same thing, we would need to multiply this guy by 4 again. Okay, you're good. And now you will basically be again subtracting 8 pi over 4, and what will this end up giving us, guys?
-7 pi.
There you go, very nice, so -7 pi over 4, and that will be our come on. Okay, so let's see. Positive angle can be this guy. For that matter, honestly, he can also be the positive angle. And then that one will be your negative coterminal. Questions, guys? So just keep in mind, it's basically how many revolutions you need to subtract or add, right? So you can start with just 2 pi, adding, subtracting, but if it doesn't give you the positive or the negative, raise that revolution. So do it 4 pi instead of 2 pi. And that's really all there is when you are trying to find coterminal angles. So let's make sure we save this. Hoping it's saved. Okay, so coterminal angles. Now let's talk about supplementary and complementary. I played around with this the other day and now I can't remember how we clean that up. Okay. So supplementary complementary angle basically comes down to, are they adding up to 90 degrees pi half? Or are they adding up to 180 degrees, which is of course pi? So as you can see in the left side figure, that if the two angles add up to 90 degrees, they are what we call as complementary angles. If they add up to 180 degrees, like the figure on the right, those are going to be your supplementary angles. So in this case, you want to think about in terms of pi halves and pi. All right, so just to show you your examples over here, we're basically saying if your angle is 2 pi over 5, then basically when you're trying to find its complementary angle, you would take that 2 pi over 5, subtract it from pi halves, because remember that represents your 90 degrees. You subtract from that and you get the answer of pi over 10. Now, keep in mind, you are not always going to find supplementary or complementary angles. And what do you think would cause you, especially with a complementary, what would be the reason you couldn't find a complementary angle?
They went too far.
Yeah, if the original angle was larger than 90 degrees, you're not going to be able to find a complementary angle. And like I said, that can be true for supplements also, because if the original angle is larger than pi or 180 degrees, you wouldn't be able to find its pair. So basically, if you're finding the complement, take the angle, subtract that from pi halves, and you'll get your answer. If you're trying to find the supplement, you subtract the angle from pi and see if you can find its pair. So you can see in part B, they're telling us there is no complement for 4 pi over 5 because that angle is already greater than pi halves. And this would be a great place to kind of use your unit circle to see where those angles might fall. Now, they're not going to give you all the angles listed over here. So you will see there is no 2 pi over 5 over here. And what was the other one we just looked at? 4 pi over 5. You won't see those over here, but as you get more used to what the radian measurements are and where they're going to fall, you will start getting a better idea of these. But of course, use the unit circle for your advantage. So let's take a look at our example here of trying to find the complement and supplement of pi over 6 and 5 pi over 6. I just realized we didn't do the part B over here, but you guys can see that in the video lectures if you wanted to see what the part B of coterminal was. So with pi over 6, can we find both complement, supplement? Yeah, where does pi over 6 fall? Which quadrant? Yeah, so it falls in the first quadrant, which means you can find both complement and supplement. So what do you think would be the complement for pi over 6?
Pi over 3.
Pi over 3? So you're basically taking pi halves, and from that you would be subtracting pi over 6. So do we concur it's going to be pi over 3? Anybody has a different answer? So again, back to algebra, guys, you would be finding a common denominator, which means you would then multiply that first angle by 3. You would end up getting 3 pi over 6. From that, you would be subtracting your pi over 6, which of course 3 minus 1 gives you 2 pi over 6. And same thing, reduce your fractions. I don't know why these colors are not working, but 2 goes into itself once, goes into 6 3 times. And that ends up giving you pi over 3. What about the supplementary angle?
Pi over 6.
5 pi over 6. Okay, so supplementary is 180 degrees or pi. So you are subtracting pi over 6 from pi. Right? So this will then end up giving us same thing. This guy is over 1. So we would multiply this by 6. So you are taking 6 pi over 6, subtracting pi over 6 from it, which would of course again 6 minus 1. Like you said, very nice. 5 pi over 6 would be its supplementary. All righty, perfect. What about 5 pi over 6? Oh. What did you not change here? Alrighty. There you go. Okay. 5 pi over 6. What will be its complement and supplement?
The supplement of 1 pi over 6.
Okay, and why does it not have a complement?
It's too far.
Yeah, because it's in quadrant 2, so it has no complement. And then what was the supplementary angle?
Pi over 6.
We actually just did that math, right? I mean, when you did the pi over 6, that's what the supplementary angle came out to be. So this is honestly the same angles we're talking about, just on the other side. So again, if you take pi and subtract 5 pi over 6 from this, again, obviously you would be doing the same math, multiply this guy by 6. You would have 6 pi over 6 minus 5 pi over 6. Which would then end up giving you 5 over 6. This is so messed up. All right. I'm not going to spend too much time talking about degrees. I'm kind of hoping you guys are a little bit more comfortable with degrees, but as you can see, you're still starting in the same direction. So counterclockwise gives you positive angles. So we're starting at the initial side with 0. You're going counterclockwise for all of your measurements, and then you come back to 360 degrees, which is equivalent to 2 pi. Think about those protractors we used to use back in school. When you measured the same way it used to go, right? It used to start with the smaller angles here. And as you made your way counterclockwise, you would be going from 0 to 180 degrees. That's exactly the same over here. So just as far as the correlation between degrees and radians goes, 360 degrees would be 2 pi radians, 180 degrees would be pi radians. And then, of course, we want to talk about conversion, going back and forth between the the degrees and the radians. So this is the conversion factor you're looking for. 1 degree is the same as pi divided by 180 degrees, or 1 radian is 180 degrees divided by pi. If you can remember even one of those combinations, you can do the conversion. So this is what you need to remember. If you are getting rid of the degree measurement and converting to pi, 180 needs to be on the bottom. If you are getting rid of the radian and converting it to pi, I'm sorry, I keep saying pi. If you're getting rid of the radian and converting it to degree, 180 needs to be on the top. So that's the difference. So you can see here, you're going from degrees to radians, which means we're getting rid of the degree. 180 degrees is on the bottom. You're going from radians to degrees, which means you're eliminating radians and going to degrees. 180 has to be on the top. So pi over 180 or 180 over pi are going to be your conversions, because again, remember, this is coming from that relationship that 360 degrees is 2 pi or 180 degrees is 1 pi. So this one over here just walks you through, the common angles. So you can see pi over 6 is the same as 30 degrees. Pi over 4, which is basically half of pi halves, is going to be 45 degrees. This is the complementary angle to this guy. So pi over 3 is 60 degrees. Pi halves is 90, pi is 180, 2 pi is 360. The larger the denominator in the radian, the smaller the degree measurement is. So you can see 6 is my largest denominator, right, out of all these fractions. and that's my smallest angle. So the larger your denominator is going to be, the smaller the angle is going to be. So pi over 6 is 30, 45, 60, 90. So just to show you the conversions here, you're going from 135 degrees. So again, we're getting rid of degrees, so we put 180 on the bottom. So you can see that means the degree measurement cancels out. You end up multiplying 135 with pi and then dividing by 180, which honestly, you're just reducing this fraction. 135 on the top, 180 on the bottom, and you're just reducing that fraction, which as you can see comes down to 3/4 pi radians. Here, 540, so you know 540 is larger than 360, right? Which means this number has to be larger than 2 pi because the original angle is bigger than 1 revolution. In radians also, you should see that. So same thing, 540 multiplied by pi divided by 180. These two cancel each other out, giving you the 3. All right, guys, let's do this. We'll do 320 degrees as a quick conversion, and then we'll call it a day for today. So we're converting 320 degrees into radians. So pi will go on the top. 180 degrees will go on the bottom. And can you tell me what this guy will come out to be? And we will need a reduced fraction. I think I left my office. The worst at home. Yeah, I think they're upstairs. Say that again. So we'll go to Desmos. And you can see under Desmos, when you go under math tools, you can get your graphing or scientific. We're just using scientific calculator. So we're trying to divide 320 by 180. By default, it's going to give you a decimal answer, but if you click on that little fraction icon, it gives you your fractions. Technology, man, makes life easy, doesn't it? So this will actually come out to be the 16 is just a bunch of 2s, right?
Yeah.
And 9 is, of course, 3 times 3, so there's nothing else common left in there. So that's how far we go. And then you can see for the radians to degrees, you're just flipping that fraction over. So I guess while we're on this, let's quickly finish one of these. Let's do, well, I don't know, 5 pi over 3. So for 5 pi over 3, you know, it's understood that this is in radians. So that means 180 will have to go on the top. And pi will have to go on the bottom. So what will this guy clean up into? And that, of course, means you're canceling out the radian measurement. You're also canceling out the pi. They'll cancel each other out. So 5 over 3 multiplied by 180, what will that give us? Now, if you were doing this by hand, 3 would actually go into 180 and cancel out, and then you can just multiply what you're left with. So let's see, we're taking 180, multiplying 5 and dividing by 3. And you can see that is coming out to be 300 degrees. So you weren't quite at 360, you were shy of that. So you're still within 1 revolution. Everybody okay with converting from degrees to radians? Yeah, and of course, you know, take a little time practicing this. You have more questions on this. Want to make sure you're comfortable. Because for some of those angles that are not on the unit circle, if you're trying to figure out where they fall on the unit circle, it would be nice to convert them into degrees, because, of course, we kind of think more in degrees because that's what we're comfortable with. By the end of this class, you guys will get comfortable working with radians also. But this would really help you while you're working through this, so you could kind of at least see, okay, what quadrant is my angle falling into? Can I find its complement? Can I find its supplement? If it has a coterminal, which it should, what would that coterminal look like? So get comfortable with some of these conversions. So we're kind of just starting out over here, guys, but I would still say use your homework to practice. Do a little bit. You don't have to go through all the questions, but at least how far we made it today, go at least and work on that so you get familiar with the program. If you have any questions, we can talk about that. But we're done for this week, so I will see you guys on Tuesday. Have a wonderful day, guys. Take care.